Hi, guys. This is Mrs. Mindy, and today I'm going to talk to you about interactions of waves. Now, in case you forgot since last time, I'm going to just go fast through what you know so far about waves. There are wave parts. The tops of the waves are called the crests, the bottoms of the waves are called the troughs. How high the waves are is called amplitude, and one wave length, like one up and one down, that's called a wavelength. A transverse wave is when the vibration of the wave is perpendicular to how the wave travels, because you can see the crests of the wave are going this way, like this way, but then the vibration is going up and down like this. So that's a transverse wave. A compression wave, also called a longitudinal wave, is when the vibration axis is the same as the travel axis. So it's kind of going forward, back instead of across. So you can see the vibration of this little red dot. It's going back and forth, but the wave is going this way, so it's in the same line of travel. Waves can have different wavelengths, and that means different things depending on whether what kind of sound it is. If it's sound or if it's light, that wavelength means different things. Hertz, abbreviated HZ, is the SI unit for frequency, and hertz is defined as cycles per second. So a wavelength is a cycle. There are other things that don't look exactly like this, but we'd still count them as waves. Okay, so this is one wavelength here, and how many of these go by in a second? That's hertz. Frequency is inversely proportional to wavelength, so that means as frequency goes up, wavelength goes down. So that's for the same speed of wave. And as wavelength goes up, frequency goes down, because if they're more spread out, it takes longer for them to go by. Okay, so let's start new material. Um, this next part is about waves interacting with the environment. And this is a cool sculpture that is in New Orleans called Mirror Labyrinth. And you can see it's steel mirrors embedded into the ground. So it gives you a weird feeling. I thought that was cool anyway. So reflection is what we call waves bouncing off of things. So here we have a flashlight bouncing light off of a mirror. It just so happens that the angle that a wave comes in is equal to the angle at which the wave goes out. So that's sort of interesting, and you can predict lots of things about that. All kinds of waves can reflect, although when we say reflection, the first thing that comes into your mind is probably like a mirror reflection. But not just light waves reflect, all kinds of waves reflect. Water waves, here I have an example of sound waves. So here's a bat yelling, and as that sound goes out, it bounces back, and it gives the bat information by the sound that bounces back, whether there is a delicious moth that it can get. Refraction is waves bending as they go through different materials, and that bend occurs because waves go through different materials at different speeds, and that causes them to bend as they go through, unless they're going through like completely straight. But if they're going through at any angle at all, it's going to bend. Okay, and you can see this. You may have seen this if you're drinking a drink with a straw, then you see that the straw kind of looks like it breaks and bends and comes over, but it's just the light. Refraction is how you know transparent things are there. Because if the light just went through and it didn't bend in this funny way, you would not even see it. So look at this glass. I guess you'd see this little reflection here. But the light bends, and you can tell when there is water in something because the water bends the light differently than the air does. So that's how you see these clear liquids and clear things, is when they bend the light. If they don't bend the light, you don't see them. Refraction is how lenses and prisms work. This is a camera lens, so you can see this blurry blob back here is revealed to be a cat when seen through the camera lens. And these colored lights, they bend and twist. So lenses are thicker in some places and thinner in other places. So that's why they bend the light in different directions depending on where the light hits it. So like here it bent it down and here it bent it up. And here's a prism here with a beam of light coming out here. And let's say a little bit more about prisms. Refraction is why prisms make spectra, which are rainbows. So as the light comes through, white light, as you may know, is all kinds of different colors of light all mixed together. But what is interesting is each different wavelength is refracted a slightly different amount by the move into a different material in the prism. So that's why it spreads the colors out, is because each of the colors bends a little bit different, a tiny different angle. And so if it hits it just right, you can spread those colors out. Refraction can happen with sound too. It's a little different to think about because we don't really experience refraction. But here's a neat example: is in dolphins. Dolphins, you know how they have that curve in their forehead right here, and that is because they have this kind of a ball of fat called a melon, and they use it as a sound lens to focus their echolocation sound. So you may know that they make echolocation too, like bats, and they make noises through the water to see further away, and they get this echo back. And so to focus that sound, they use this part of their body, which is pretty cool. Okay, waves can also interact with other waves with interesting effects. Um, Constructive interference is when two waves add together. So you can see in these two waves, the crests line up, the troughs line up, they have the same wavelength. And so then they add together. You can see the amplitude of these. This resultant wave goes up. The wavelength is the same, but um, the amplitude goes up. Now, constructive interference may not be exactly, they don't have to be like perfectly lined up, but it's anything where it's adding and um, making the wave bigger. So that's constructive interference, higher amplitude. On the other hand, destructive interference is when waves cancel. So you can see here that the crest of this wave lines up with the trough of this other wave. And as you're adding those together, it happens that they cancel out with this one. Okay. Now this is kind of a weird thing to realize. So the to think that you can have a sound and then another sound cancels it and makes no sound. But this is really true. This can really happen. You may have heard of noise canceling headphones, and they are cooler than you may think because noise canceling is different than noise muffling or noise blocking. So, the noise canceling headphones, why they're so expensive, is that they have little microphones on the outside that hear the ambient noise and then create a sound that absolutely opposes that and causes destructive interference. So it cancels out the sound. So that is strange to me and interesting. Okay, resonance. Resonance is when one wave or one force can add to a wave a little bit at a time, a little bit at a time by adding it at just the right time. Okay, so the most common example that you may have heard of, that you may be the most familiar with, is swinging on a swing when somebody pushes you. So you know how you have to push someone at just the right point. So it's just the right time when they just come back up and they're at their highest point, and then you push them forward when they're already going forward. And it kind of sounds funny because, of course, you know how to do this. But you can imagine that there would be ways that would be bad that you don't push, and sometimes you could see, like, little kids trying to push each other, and one little kid will, like, shove the other kid, like, off the swing accidentally because they didn't add it at the right way. So, um, your push frequency has to be the same as the swing frequency for the push to help. And this is true for all kinds of resonance. Like it just has to add it. So the wavelength, if you think about your pushing as having a wavelength because you're going push and then not pushing, push, not pushing, push, not pushing, push, not pushing. That has to line up with the right place of the swing frequency. So the crests of those things kind of have to line up for this to work. And that's true for all resonance things. And there are all kinds of different things about resonance that make, but they all result in the amplitude of the wave getting bigger, the resultant wave. So it's a constructive interference. So even a small force applied at the right point can add up through resonance. So like this little kid here is pushing their big dad because they can add it at just the right time. It can be a little bitty force and still make it move. The Doppler effect. So you have heard the Doppler effect, and like if you've heard a car or a fire truck or a train or something going by, and you get this effect where it goes like that. And have you ever thought that the car is making the same sound? It's just that the car is in motion that you get this Doppler effect. So you can kind of think of this as the effect. Here is what is happening with that. So as you have a moving source of the waves, it squashes the waves up ahead of the motion and it stretches them out behind. Okay? So what that sounds like to you is so the wave source is moving this way. You get a higher frequency on the one side. And remember, higher frequency with sound sounds like a higher pitch. And then behind where the source is moving, you get a lower frequency, so a lower pitch. We can also tell this with light. So we know that faraway galaxies are moving because of the Doppler effect. So imagine that there's a galaxy and that it is moving toward us. It's far, far away, but it's moving toward us. Its light is going to get squashed up more from the Doppler effect because it's moving toward us, and squashed up in light means more toward the bluer end of the spectrum. So whatever color it is, it'll move more in the blue direction. So we call that blue shift if it's coming toward us. If the galaxy is going away from us, say, if you're a viewer over here, and it's going away from us, then that light gets stretched out. It gets longer, and the longer end of the spectrum is red. So we call that red shifted. Here is this is from a research paper. So this is not like from a movie or anything. This is from a research paper. A group of galaxies. So each of these little things are not stars. Each of these little smeary things are galaxies. Each one is a galaxy. And what the researcher has done is they have tinted them to show if they are coming towards us, and the blue ones are coming towards us or moving away. The red ones are moving away. And they're different sizes and they're different locations in space. So that's just kind of like a cool thing that astronomers are doing all the time is looking at the shift in the Doppler shift in the light that's coming to us. So an interesting thing to note, the Doppler shift in faraway objects was why the Big Bang idea was developed. It was discovered, and when researchers, it was Hubble, who like Hubble Space Telescope, but it was named after him. He was from long ago, and he noticed this, and he was like, "What is this? Why are these red shifted, and why are these blue shifted?" And he said, "Well, okay, that could be explained by the universe expanding. And if the universe is expanding now, that means it must have been smaller before. And if you take that back, that's was why the idea of the Big Bang came about, because the universe used to be squished down into a tiny, tiny thing." Okay, that's it for today, and I will see you next time.